Welcome to the debate. Today, we are diving into really a foundational question in modern systems engineering. It's centered on the architectural analysis of the Polystore key value system. Now, this system is famous, or maybe notorious, for its conscious choice of a heterogeneous technology stack. We're talking Rust for the storage engine, Go for the API server, and then Python for the client. It's kind of the quintessential example of that right tool for the job philosophy. So the real question, I think, for anyone designing a scalable modern system is this. Does achieving that specialized performance, through a polyglot architecture, does it actually pay off? Does the technical purity, the optimization you gain by using Rust and Go in their sort of perfect niches, does that justify the significant organizational, operational, and frankly, talent acquisition friction it inherently introduces? I come to this debate arguing that, well, the technical choices are brilliant, they're empirically validated, and that this design is actually exemplary for maximizing critical component efficiency.
And I look at this issue from a completely different angle. While I fully respect the elegance of the technical design, the performance metrics are pretty undeniable. I focus more on the global cost of ownership. I'm convinced that the non-technical costs, the ones associated with system complexity, organizational overhead, and just managing all that heterogeneity, they ultimately render the polyglot approach strategically unsound, especially when moving from a proof of concept to a reliable, scalable production system. Local optimization often leads to systemic trouble down the line.
Okay, let's start with the foundation then, because this is where Polystore, I think, truly shines. The design selection of three distinct languages, it's absolutely sound and it's data-driven. For the storage engine, we see Rust, and this is really a non-negotiable requirement for technical fitness. Why? Well, because the storage layer demands predictable low latency and absolute stability. The genius of Rust here is that it gives a C++ level performance while critically eliminating the garbage collector. This avoidance of GC means we never have those dreaded stop-the-world pauses where the entire database just freezes for milliseconds to clean up memory. For a high-performance database, avoiding those latency spikes, that's everything. And, its ownership model, it provides compile time guarantees, preventing an entire category of incredibly difficult to diagnose memory bugs like dangling pointers or data races that often plague systems written in C or C++. This is safety at speed, which is absolutely paramount for the core data layer.
Right. I see why you prioritize technical perfection for that layer. And the argument against GC latency spikes is certainly compelling. But you're focusing really intensely on the micro-level performance metrics. Let's look at the other side of the stack for a second. Go is indeed fantastic for the API server, no question. It's tailor-made for high concurrency, I/O-bound tasks. Its Go routines and channels allow it to handle, thousands upon thousands of simultaneous connections far more efficiently than, say, a traditional thread-based model. But this is the start of what I call the polyglot paradox, that micro-optimization leading directly to systemic, global complexity. The operational friction this introduces is immense, and it's not just additive. The complexity feels, exponential. You can't just add up the cost of managing the Rust, Go, and Python environments separately. You have to have three completely separate, distinct build pipelines, test pipelines, dependency management, deployment pipelines, the whole works. You've got Cargo for Rust, the Go toolchain for the API, and then a whole separate set of Python packages and environments. Managing the inter-service communication and integration testing across these three disparate runtimes, it demands a huge investment in let's call it a highly mature DevOps culture, just to tread water and keep the environment operational. That overhead is the massive hidden tax on your pure technical optimization.
Okay, I recognize the friction you're pointing to, but I'd argue that friction is the necessary cost of engineering a truly optimized system. Let's return to the core function, reliability. Rust's predictable performance, that's a non-negotiable requirement for that storage layer. If we chose Go or, say, Java, you accept the fact that your database engine will occasionally spike in latency because the GC inevitably runs. We invest in Rust not because we just love complex toolchains, but because it solves a critical stability problem that GC-based languages simply cannot guarantee for true systems programming. The data really validates that investment.
That's a compelling argument regarding the stability gained. I'll grant you that. But let me shift the focus from machine latency to the human cost. This commitment to 3 separate languages creates these rigid knowledge silos within the team. What we often call the bus factor becomes dangerously high, and that is a really insidious cost to the business. I mean, think about it. If a developer has deep expertise in Go and the API server, they may be completely, unable to contribute effectively to the Rust-based storage engine without weeks or even months of ramp-up time, assuming they even want to learn Rust, which isn't guaranteed. This severely compromises organizational resilience. Your critical component, the storage engine, becomes reliant on a very small, specific talent pool. If that key Rust expert leaves or is simply unavailable for whatever reason, your system is exposed to a significant, acute business continuity risk that, I argue, far outweighs the few milliseconds of latency you might have saved.
I recognize the bus factor is a genuine constraint, but I would argue that's more of a staffing and knowledge sharing issue, not necessarily an architectural failing. And frankly, the productivity gains we see in other parts of the stack can often offset that risk. Consider the client layer. We use Python there. Why? Because Python's exceptional ease of use and rapid development, developer ergonomics, perfectly align with the goal of creating an intuitive user interface where complexity is relatively low and iteration speed is high. Its slower execution speed is completely irrelevant in this context because the heavy lifting is done by the high-performance server components. We choose the language based on the layer's primary constraint, productivity for the client, concurrency for the API, and that critical low latency for the storage engine. This feels like a modern, pragmatic trade-off that maximizes developer velocity where it matters most.
That's a thoughtful defensive developer ergonomics at the client layer, sure, but I think you are minimizing the strategic difficulty of hiring across the entire heterogeneous stack. It's one thing to hire a single language specialist, right? But finding a candidate with deep production-level expertise across that specific Venn diagram, Rust for low-level systems and Go for microservices, and Python fluency, that is exponentially harder. The analysis itself stated that finding this kind of multi-specialist talent is an order of magnitude more difficult and expensive. And this burden is acutely felt by any organization that lacks the vast recruiting resources and, let's be honest, the massive brand recognition of the largest tech companies. By adopting polygloticism, smaller or growing organizations fundamentally constrain their ability to scale their engineering teams quickly. You might be choking off growth capacity in the long run. You've potentially created a beautifully efficient system that maybe only 3 people in the world can effectively maintain.
Well, okay. If we are going to talk about managing heterogeneity, we need to talk about how Polystore actually addresses it via communication. The design demonstrates, I think quite maturely, that this language mix can be managed robustly by adopting dual communication standards, what the paper calls API bimodality. Internally, between the Go API server and the Rust storage engine, they use gRPC. Externally, for general client access, they use REST. Now, gRPC provides the essential performance backbone. It's built on HTTP2, uses protocol buffers for serialization. This means you get significantly higher throughput, up to maybe 2.5 times higher, and lower latency, maybe 2 to 3 times lower, than traditional REST JSON communication. Crucially, protocol buffers result in incredibly small binary payloads, sometimes up to 50% smaller, which significantly reduces network bandwidth usage and improves that internal performance. This shows that complexity is being managed effectively and performance is prioritized right where it matters most, between the core components.
I wholeheartedly agree that gRPC is superior to REST for internal communication. That's absolutely the right protocol choice there. But focusing on the wire speed kind of misses the larger point of systemic complexity, doesn't it? You're measuring the efficiency of the connection, not the difficulty of the debug process when something goes wrong. Even with optimized gRPC traffic, debugging becomes a formidable challenge precisely because you still have 3 separate, distinct language runtimes in play. Tracing a single user request requires correlating logs and metrics from distinct logging frameworks across multiple machines. Rust has its logging ecosystem like log and tracing, Go has its own standard library and frameworks, and Python has a whole third set, linking those logs, managing distributed tracing IDs consistently, ensuring metrics collection is uniform across these heterogeneous environments. It demands an incredibly expensive and sophisticated observability platform. Every time you switch toolchains in that trace path, you increase the cognitive load and, critically, the operational failure surface. High throughput is kind of irrelevant if you can't efficiently find the root cause of an outage at 3 a.m.
You are arguing that the cost of observability outweighs the performance gain, but I see the V1.0 design differently. I see it as a successful and necessary technical foundation. It proved the core principles could work. I mean, look at the planned roadmap for V2.0 they outlined. Implementing Kubernetes, adding Raft consensus for fault tolerance, sharding for horizontal scaling. These are heavy distributed systems challenges. Building a robust distributed system requires strong, high-performance, and reliable components at its core, and V1.0 successfully delivered that foundation. The technical choices like the LSM tree for write optimization, the selection of Rust specifically for stability, these are solid engineering decisions that lay the groundwork for a truly scalable, multi-node architecture.
You know, that roadmap for V2.0 is actually my strongest piece of evidence against the strategic viability of V1.0's polyglotism. When the rubber meets the road, right, when the system moves from being a high-performance prototype to a production system that must be maintained day in, day out by an actual team, the report authors themselves suggest the direction changes significantly. The strategic recommendation for the V2.0 production team explicitly suggests they should consider standardizing on a single, high-performance, general-purpose language like Go or Rust for both the API server and the storage engine. And why? To quote them again, to significantly reduce operational overhead and ease the burden of hiring. This tells us everything, doesn't it? Technical purity, while maybe brilliant for a learning exercise or a proof of concept, is often, and I'd argue rightly, discarded for organizational and operational pragmatism when it comes to scaling and maintaining reliability in the real world. The architecture you champion, while technically elegant, is ultimately deemed too costly to survive into production maturity.
My argument remains that the technical justifications for these polyglot choices are empirically validated. They lead to an exemplary architecture that maximizes performance precisely where that performance is most critical. The friction we've discussed, yes, it exists, but it's a quantifiable and manageable engineering cost. It's the necessary price, perhaps, of building a truly highly optimized system.
And my position remains that the polyglot paradox proves that the most technically optimal solution for individual components can actually be the least viable strategic choice for the organization as a whole. You might gain milliseconds in latency, sure, but you potentially lose months in hiring cycles, and you definitely lose hours every week just to operational overhead and complexity management. The long-term viability of the system, I believe, is compromised by the exponential friction it creates for the people who actually have to build, staff, and debug it under pressure.
Well, this discussion certainly illuminates the critical trade-off, I think, that sits at the heart of distributed systems design. That age-old battle between maximizing specialized component performance and minimizing the overall cost of ownership and the organizational friction involved.
Absolutely. It's a tension every engineering leader has to face, probably daily. The source material here offers valuable insight into how technical purity often conflicts, sometimes sharply, with production reality. And it leaves us all with the question of which constraint truly matters most when moving a system from a prototype stage to a robust platform.
Thank you for joining us on the debate.